Hello friends, good afternoon. Welcome to CEC live lectures. Dear friends, in this session we will be continuing our lecture series on mathematical methods for economics. And in this series, today we would be talking on absolute value. To discuss this topic, we have our subject expert, Dr. Niti Bhutani with us. Dr. Bhutani is Assistant Professor, Department of Economics, Hindu College, University of Delhi. So, Dr. Bhutani has contributed various articles in news terms and in various policy reports. So, without wasting much time, I would like to welcome ma'am to our studios and request her to start the lecture.
Thank you very much, Asmita. Hello everyone, I welcome you to our lecture series on mathematical methods for economics. This is our fourth lecture in the series, and the topic for today's lecture, as Asmita just pointed out, is absolute value. I will start the lecture by defining and explaining the concept of absolute value. And on a related note, I will also be talking a little bit about the square root of a real number, because this is a concept which is related to the idea of absolute value. But a large part of this lecture will be devoted to practicing equations and inequalities that involve absolute values, and if time permits, square roots also. These are the kinds of questions, in fact, that typically appear on a test or an exam if you were to write on this topic. And I hope that the problems that I have selected for you are representative enough, and you will get good practice after looking at these problems. So first things first, let us introduce the idea, the concept of absolute value. Let us assume that we have a real number x. If you look at this slide, then the absolute value, or the modulus of x, or the mod of x as some people also call it, is denoted by writing, this is a notation, we write x with vertical bars on both sides. Now, before I show you the expression for the absolute value of x that you are so used to seeing from your school days, let me first introduce the definition of absolute value, and you'll see in a bit how that definition automatically leads to the expression that you are so familiar with. So, as I was saying, let us assume that x is a real number, and you can imagine it as a point on the number line. Then the absolute value of x is the distance between that number x and 0 on the number line. So this is a distance concept, and before I get into specifics, let me just state at the outset, because distance is never negative, so the absolute value of this number x, whichever number we are taking, is never going to be negative. It's always going to be greater than or equal to 0 for all values of x. Now, getting into specifics, we have said that the absolute value of x is the distance between x and 0 on the number line. Now, this number x that we are visualizing, there are two possibilities as far as this number is concerned. The number x could be non-negative, it could be greater than or equal to 0, or the second possibility is that this number could be negative. Let us take the first possibility into account. Let us suppose the number x is non-negative. It is greater than or equal to 0. In particular, let us assume that x is equal to 4. Then the mod of 4, the absolute value of 4, is the distance between 4 and 0 on this number line that you can see on this slide, and I have marked this distance by this green line here, and you can see that the distance between 4 and 0 is 4 itself. Therefore, the absolute value of 4 is 4 itself, or in general, whenever we take a number which is greater than or equal to 0, the absolute value of x is the number itself. Let us now look at the second possibility, where x is negative. In particular, let us assume that x is equal to minus 4. So now the absolute value of minus 4 is going to be the distance between minus 4 and 0 on the number line. and that you can see is this green line here, and as before, the distance between -4 and 0 is still 4 units. Therefore, the absolute value of -4 is now given by minus of -4, because we have to convert it into, we have to bring in the distance aspect. So the absolute value of -4 is minus of -4, which is equal to 4. In general, if x is a negative number like we just saw, then the absolute value of x is equal to minus of x, because x is a negative number. If we put a minus in front of it, that will automatically become positive, and that will then represent the distance between x and 0 on the number line. These two cases can now be combined to see what the absolute value of x expression is, and this is what you would be doing in school as well. So the absolute value of x is equal to x if x is non-negative, and it is equal to minus x if x is negative. Please note here that the weak inequality, when we write x greater than or equal to 0, that is by convention written on top, and we take a strict inequality at the bottom. This is just in terms of presentation. Now, if we look at some examples, so as I just said, the absolute value of 4 is 4 itself, because that's the distance between 4 and 0 on the number line. Similarly, the absolute value of -4 would be 4 again, because the distance between -4 and 0 on the number line is again 4. Similarly, the absolute value of 7 is 7. The absolute value of -1/3 will be the distance between -1/3 and 0 on the number line. So that will be 1/3, and that will be given by minus of -1/3. Finally, the final example here is that the absolute value of 0 is 0 itself, because you are bang on 0. Let us see if we can start working with the definition of absolute value as given here. So the first example asks you to rewrite the absolute value of x minus 3 using the definition above. So what we have to do here is, if you notice that in the definition we have an x inside the absolute value sign. Now, whatever we did for x in the definition, for this example, we will perform the same kind of exercise for x minus 3. So the absolute value of x minus 3 will be given by x minus 3 if x minus 3 is non-negative. So instead of x, I'm just writing x minus 3 everywhere. And the absolute value of x minus 3 is minus of x minus 3 if x minus 3 is negative. Now, if you notice here on the right side, I can further simplify these inequalities, because x minus 3 greater than or equal to 0, if you see where my cursor is pointing, this can be written as x is greater than or equal to 3. So in this way, if we simplify the expression, I get that the absolute value of x minus 3 is equal to x minus 3 if x is greater than or equal to 3, and it is equal to minus of x minus 3, or it is 3 minus x if the number x is less than 3. Let us also give some interpretation to this expression for the absolute value of x minus 3. Now, just as the absolute value of x represents the distance between x and 0 on the number line, similarly, the absolute value of x minus 3 represents the distance between x and 3 on the number line. And you can see how this is true. Let us take some examples here. If suppose x is equal to 6, then you can visualize the number 6 on the number line, and you'll see that the distance between 6 and 3 is 3. So if we take the absolute value of x minus 3 here, and you can check that that absolute value is also equal to absolute value of 3, which is 3. Because x is 6, so x minus 3 will be 3, and the absolute value would then give you a 3. Similarly, if x is equal to minus 4, then you can again visualize the distance between -4 and 3 would be 7 units. They'll be 7 units apart, and that is exactly what you get when you take the absolute value of x minus 3. So if you look here, if I put x equal to -4, then -4 minus 3 is equal to -7, and the absolute value of -7 is 7. Finally, we see here that if x is equal to 3, then the modulus, the absolute value of x minus 3 is equal to 0, which indicates a 0 distance from the number 3. In general, we can write that the absolute value of x1 minus x2 represents the distance between the numbers x1 and x2 on the number line. Okay, let's do just one more example to just make sure that you are comfortable with the definition. Now, this example asks you to rewrite 2x plus 1 using the definition of absolute value. So again, instead of x, we are going to write 2x plus 1 in the definition. So the absolute value of 2x plus 1 is, as you can see here, it is equal to 2x plus 1 if 2x plus 1 is greater than or equal to 0, and it is equal to minus of 2x plus 1 if 2x plus 1 is negative. And this can be simplified to write as follows. The absolute value of 2x plus 1 will be 2x plus 1 if x is greater than or equal to minus half, and it is equal to minus of 2x plus 1 if x is less than minus half. We should also be able to work our way backwards when we are working with absolute values. So suppose I tell you that the absolute value of a number x is equal to 4, and I ask you what are the possible values that x can take, then here you should be able to tell using the definition that x could be 4 or x could be minus 4, because if I take the absolute value of 4 or minus 4, the absolute value is going to be 4. And in general, if the absolute value of x is equal to some number a, where a is, I'll just mention that a is going to be non-negative. So if a mod of x is equal to the number a, then this means that if I solve for x, I will get x is equal to a or x is equal to minus a. And please note here that this number a in this equation must be greater than or equal to 0, because if it is negative, then if you look at this equation, mod x will become equal to some negative number, and mod x, as I just said in the beginning of the lecture, it can never be negative. It represents distance, and therefore distance, because distance is always greater than or equal to 0, the number a has to be non-negative. Right. At this point, I would also like to show you this result, which is something very important, and it says that mathematically the absolute value of x is equal to the square root of x square. This is actually a very important result, and it is used for some proofs that we'll be doing in the future lectures, and also it helps give some clarity on the idea of a square root. And let me give some perspective here. So when I teach this class, when I teach this topic in particular, I ask my students this question. So I ask my students, what is the square root of 9? And I have been teaching this course for a number of years, but not even once have I got one answer. It's always the case that I get two sets of answers. So I have one set of students that will say that the square root of 9 is plus minus 3, and then there is another set of students who will say that the square root of 9 is plus 3. So the question is the square root of 9 plus minus 3, or is it plus 3? And the answer here is that the square root of 9 is plus 3. So please note this, and the way to think about it is in terms of this result. So, so as I was saying, the square root of 9 is plus 3. So the way to think about it is, if you look at the absolute value of x here, we are saying the square root of x squared is equal to the absolute value of x. Now, because absolute value can never be negative, therefore the square root here always has to be the positive square root. This square root here is also known as a principal square root by many mathematicians. So the point here is that because the absolute value of x cannot be negative, we cannot take the square root of 9 as plus minus 3, we have to take it only as plus 3. Similarly, the square root of 4 is 2, the square root of 16 is 4, and so on. So this is a very important point that you should take note of. Another way to look at this idea is that suppose I have the equation x is equal to square root of 4. Now in this equation, if you look at where my cursor is pointing, in this equation there is only one value of x for which we can find the square root, and that value of x is going to be 2. However, if we are looking at the equation x square is equal to 4, then in this case if we solve for x, we will get x is equal to plus 2 or minus 2. Alternatively, x is equal to plus square root of 4 or minus square root of 4. But the point is that the square root of 4 is still 2. So the idea here is, if I am looking at the equation x is equal to square root of 4, then x is equal to 2. But if I am looking at the equation x square is equal to 4, then the unknowns that I am solving for could be either 2 or minus 2. Another point that I would like to make in this lecture is that as far as this course is concerned, we will not be considering square roots of negative numbers. In this course, we only focus on the real space, the real number space. We'll only be dealing with real numbers. So the expression under the square root has to be non-negative, because if it is negative, then you'll enter the world of complex numbers, imaginary numbers, and in this course we don't deal in imaginary numbers. So as far as this course is concerned, please make sure that whatever expression you have under the square root sign or the radical sign, that should be greater than or equal to 0. It should not be negative. And to see this formally, suppose we are taking the square root of a number a, and let's call the square root x. Then squaring both sides will give a is equal to x square, and x square is always greater than or equal to 0. So therefore a also has to be greater than or equal to 0. We will now be looking at a very important property of absolute value, and this is something which we'll be using a lot when we solve inequalities. So please pay attention here. Let us suppose we have a number a which is positive, then the absolute value of x less than a, the inequality mod of x less than a, means that x lies between minus a and a with strict inequalities on both sides. Now let's first look at it, let's first interpret this result intuitively before I give you the formal proof. When I say that the mod of x is less than a, here I am saying the mod of x is the distance between x and 0 on the number line. So when mod of x is less than a, what I am saying in words is that the distance between the number x and 0 on the number line can't be more than a. And you can see here on this number line that the distance will be less than a, or at most a, only when x lies between minus a and a. You can see here on the green line, if x is in this interval between minus a to a, then only the distance between the number x and 0 will be less than a, or at most a. But if you take a number x to the right of a or to the left of minus a, where my cursor is, then the distance will become more than a. So that is why intuitively the solution x has to lie between minus a and a. We can also look at the proof here. So whenever we are dealing with modulus signs, there are two cases that emerge. So the first case is the one where x is non-negative. So if x is greater than or equal to 0, then the absolute value of x is equal to the number x itself. Therefore, the inequality mod of x less than a will boil down to x less than a. Then in the second scenario, suppose x is negative. In that case, the absolute value of x is equal to minus x, so that our inequality mod of x less than a boils down to minus x less than a, which in turn implies that x is greater than minus a. If I multiply the inequality on both sides by a negative, then I have to reverse the inequality. So x becomes greater than minus a, and combining the two cases then gives me the result that x lies between minus a and a. Right, let's extend this result further. So if we have the inequality mod of x greater than a now, which is to say that the distance between x and 0 is more than a, then as I just explained on the previous slide, then this means that x either has to lie to the right of a, you can see it on the slide here, the green lines are showing, so x can be either to the right of a or to the left of minus a, and any number x on the green lines will give you distance which is more than a on the number line. And the proof for this is along similar lines. If x is non-negative, then the mod of x will be x, so that our inequality becomes x greater than a. And if x is negative, then the absolute value of x is minus x, and in this case minus x, the original inequality mod of x greater than a becomes minus x greater than a, or x less than minus a. And again, combining the two cases, we get the result that x is greater than a or x is less than minus a. And finally, we can use this property, the properties that I just mentioned, with weak inequalities also. So in this case, let us suppose we have a number a which is non-negative, then mod of x less than or equal to a means that x lies between minus a and a with weak inequalities, and mod x greater than or equal to a means that x is greater than or equal to a, or x is less than or equal to a. The advantage here of modifying the previous properties is that this also allows a to be 0, which is something we were not factoring in the previous discussion of the properties. So this is as far as the properties of absolute properties relating to absolute values are concerned. I've just done 2 so far. I'll be doing the rest in another lecture when I start discussing functions. So, but for today's lecture, this should be sufficient for at least solving your inequalities. Okay, so now we will move on to solving some equations and inequalities. Our first equation is solve the equation, our first question is solve the equation or absolute value 5 minus 2x is equal to 7 for x. Again, we'll look at the definition of 5 minus 2x, mod of 5 minus 2x first. So by definition, the absolute value of 5 minus 2x is 5 minus 2x itself if 5 minus 2x is greater than or equal to 0, and it is equal to minus of 5 minus 2x if 5 minus 2x is less than 0. And as I mentioned before, these inequalities here where my cursor is pointing, these boil down to 2 cases. The first one where x is less than or equal to 5 by 2, and the second one where x is greater than 5 by 2. So let's examine these 2 cases separately, and we'll look at what results we get, and we'll combine the 2 cases to find our final solution. Our first case is one where x is less than or equal to 5 by 2. Now, if that is the case, then the absolute value of 5 minus 2x is 5 minus 2x itself, and in the original equation we'll substitute 5 minus 2x and put that equal to 7. So solving this equation, if I take 2x to the right hand side, I get 5 minus 7 on the left hand side. So solving for x, I get x equal to minus 1. And the second case is one where that allows for the possibility that x is greater than 5 by 2. And as we just noted in the definition, if x is greater than 5 by 2, then the absolute value of 5 minus 2x is minus of 5 minus 2x. So in this case, let us now put minus of 5 minus 2x, which is 2x minus 5. Let us put that equal to 7. And now solving for x, I'll add 5 to both sides, and I'll get 2x is equal to 12, or x is equal to 6. And finally, combining both these cases, I get my solution that x equal to minus 1 or x equal to 6 will solve the equation absolute value of 5 minus 2x equal to 7. The next equation is absolute value of 5 minus 2x is equal to 0. Now, because we have a 0 on the right hand side, the way to think about this equation is that it's only the absolute value for 0 which is 0. So therefore, the expression that lies inside the absolute value sign must also be 0. Therefore, we have that 5 minus 2x is equal to 0, and therefore this implies that x is equal to 5 by 2, and that is our solution. So we have now come to the end of this first segment. I still have some more equations and some inequalities for you, but we'll do that, all of that, after a short break.
Thank you so much, ma'am. Thank you, ma'am, for this session. Dear friends, we will be continuing this session in a short while, so stay tuned and keep watching. Thank you so much. Welcome back, friends, and now we'll continue with the session what we are having in the first session, that is absolute value. So I would like to request ma'am to continue with the session. Please continue, ma'am.
Thank you very much, Asmita. Welcome back, viewers. Let's get down to our equations again. Before the break, I was talking about the equation absolute value of 5 minus 2x is equal to 0, and we were solving that for x. So I said that because the absolute value of 0 is 0, our 5 minus 2x expression must also be 0, which is to say x is equal to 5 by 2. So actually this is a very simple way and a straightforward way of solving this equation. Alternatively, you could also build up your two cases the way we usually do for a modulus expression, and I'll quickly walk you through the solution which I have prepared, an alternative solution. Even though it's long, but it gives you a sense of how to tackle things, because sometimes you end up with a contradiction in a particular case and you don't and you want to take care of that. So if you look at this expression, the absolute value of 5 minus 2x, which is what we saw earlier, is 5 minus 2x if x is less than or equal to 5 by 2, and it is equal to 2x minus 5 if x is greater than 5 by 2. So our two cases here become, the first one being x is less than or equal to 5 by 2, and if that is the case, the absolute value becomes 5 minus 2x, and the equation becomes 5 minus 2x equal to 0. If we solve this equation, we get 5 by 2, and here you can see that this is consistent with the assumption that we are making about x, which is x is less than or equal to 5 by 2. But in the second case, there's a slight issue, because in the second case our assumption is that x is strictly greater than 5 by 2. Now here in this case, the absolute value of 5 minus 2x, which is the left hand side of our equation, is 2x minus 5. Now when I put 2x minus 5 equal to 0 and I solve for x, I again get x is equal to 5 by 2, but this is something which is not allowed for by our assumption. Our assumption in this case was x is strictly greater than 5 by 2. So this case would be ruled out, but overall our result would still be x is equal to 5 by 2. These kinds of contradictions with assumptions do happen at times, and this is something you must watch out for. Right, the next equation is quite interesting. It's a little different from the usual stuff, and this equation says that the square root of x plus 4 the whole square is equal to x plus 4, and you have to solve this equation for x. Now here if you notice, this is an equation which you can easily solve by the result, using the result that I just gave you a few slides before, which is that the square root of x square, if you see where my cursor is pointing, the square root of x square is mod of x. So I have on the left hand side of this equation square root of x plus 4 the whole square, and by definition this then becomes equal to mod of x plus 4. Now we know that the absolute value of x plus 4, mod of x plus 4, is equal to x plus 4 if x plus 4 is greater than or equal to 0, and absolute value of x plus 4 is minus of x plus 4 if x plus 4 is less than 0. So if you notice here, this particular definition is actually giving you the result for the equation that you have to solve, because the top part of this definition, if you see where my cursor is pointing, is the right hand side of our equation. So we can say that this equation is satisfied when x plus 4 is greater than or equal to 0, or x is greater than or equal to minus 4, because square root of x plus 4 the whole square is mod of x plus 4, and that is equal to x plus 4, if you see where my cursor is pointing, only when x plus 4 is greater than or equal to 0. So our answer is x is greater than or equal to minus 4. Right. The next equation is also quite interesting in the sense that it has something new to offer. So if you look at this equation, this is what you have to solve for x in the equation mod of x minus 2 divided by 2x plus 5 is equal to 6. Now, as a do-it-yourself kind of exercise, I would ask you to check that if you have two numbers x and y, then the absolute value of x divided by y is equal to the absolute value of x divided by the absolute value of y. So this is a way of coming out of this absolute value in steps. And here also you can take four cases. You can take the case where x and y are both non-negative, the second case where x is non-negative but y is negative, the third where x is negative, y is non-negative, and the fourth where both x and y are negative. And you can check for yourselves that on both sides of this equation you will get the same expressions. So using this result, my equation simplifies to mod of x minus 2 divided by mod of 2x plus 5 is equal to 6. So this is the equation we're going to work with. Now again, at the outset, let us note that x can't be equal to minus 5 by 2, because if you remember in one of the earlier lectures I told you that division by 0 is not allowed. In fact, this is the first thing that you must look out for whenever you're solving equations or inequalities. If there is any number that involves a division by 0, please rule out that number immediately. So here we'll rule out x equal to minus 5 by 2 as part of the solution. Now, we have two absolute value expressions. One is mod of x minus 2 and the other is mod of 2x plus 5. And the absolute value of x minus 2 is x minus 2. If x is greater than or equal to 2, it is 2 minus x. If x is less than 2, absolute value of 2x plus 5 is 2x plus 5. If x is greater than minus 5 by 2, and now you note here I have ruled out x equal to minus 5 by 2 in this inequality, and the mod of 2x plus 5 is minus of 2x plus 5 if x is less than minus 5 by 2. This then gives rise to four possible cases. We can combine the inequalities in the following manner. One case is where x is greater than or equal to 2 and x is greater than or equal greater than minus 5 by 2, and if we combine these two we get x is greater than or equal to 2. The second case is one where x is less than 2 and x is less than minus 5 by 2, which in turn give us the intersection as x less than minus 5 by 2. The third case is where I take x greater than or equal to 2 in the first absolute value expression and x less than minus 5 by 2. But if you notice here, there is no intersection here. You can't have x more than 2 and less than minus 5 by 2 or minus 2.5 at the same time. So the third case is ruled out. And the fourth possible case is where x is less than 2 and x is greater than minus 5 by 2. So in this case, we have that overall x will lie between minus 5 by 2 and 2. Okay, so with these four possible cases, let's see what our solution would look like. The third case in any case is ruled out now. Now, if you look at the first two cases give rise to a situation where both the absolute value expressions will have the same sign. So the first case, both the absolute value expressions will be positive, and in the second case, both the absolute value expressions in the numerator and denominator are negative. So basically the signs will, the negatives will cancel out. And this then gives you the equation which I have on here on the left. X minus 2 is equal to 6 times 2x plus 5. The last case that I was exploring was one where x is less than 2 and at the same time x is greater than minus 5 by 2. So in this case, the numerator the absolute value expression in the numerator will be negative, which then gives us the equation minus of x minus 2 is equal to 6 times 2x plus 5. Now if you solve these two equations one by one, let's see what we get. On the left hand side, I have x minus 2 which is equal to now 12x plus 30, and if I take 12x to the left hand side and 2 to the right hand side, I get minus 11x is equal to 32, or x is equal to minus 32 by 11. Now solving the equation on the right hand side, I get 2 minus x is equal to 12x plus 30, which in turn means if I take 12x to the left hand side, I get minus 13x, which is then equal to 28, or x is equal to minus 28 by 13. Now if you notice, these values are minus 2.9 approximately and minus 2.15. So if you compare with the cases that we had built up here, the first one is consistent with case B, which is minus 2.9. So x less than minus 2.5 would cover minus 2.9, and our second solution is minus 2.15, which is consistent with case D, because x has to lie between minus 2.5 and 2 here, and minus 2.15 lies well within that inequality. So our solution is x is equal to minus 32 by 11 or minus 28 by 30. We will now look at some inequalities for absolute values, and the first one is the absolute value of x minus 3 is less than or equal to 5, and here we can use the property that we had stated in a few slides before this, that when mod of x is less than a, that means x lies between minus a and a. So when I have mod of x minus 3 is less than or equal to 5, it means that the expression inside the absolute value sign x minus 3 has to lie between minus 5 and 5. Now once I have this inequality, all I have to do is add 3 to all the 3 expressions here. So I get minus 5 plus 3, which is minus 2, is less than or equal to x is less than or equal to 5 plus 3, which is 8, and therefore that is our solution. X lies between minus 2 and 8. The next example asks you to solve this inequality, which is absolute value of x square minus 2 is less than or equal to 1. Again, we'll use the same property that we had outlined earlier. The absolute value of x square minus 2 less than or equal to 1 means that the expression inside the absolute value sign must lie between minus 1 and 1. And here we'll use weak inequalities because that's what the original inequality states. Now once we have this x square minus 2 lying between minus 1 and 1, I can solve this further by adding 2 to all the 3 expressions, so that I get minus 1 plus 2 on the left hand side, which is 1, is less than or equal to x square, which is less than or equal to 1 plus 2, which is 3. So in our inequality, we must have that x square lies between 1 and 3. But our job is not done yet. We have only solved for x square right now. We know where x square will lie, but we still don't know what x is. So we have to work on this range of x square, this range for x square a little bit more. Now this inequality here, where my cursor is pointing, is saying that x square is greater than or equal to 1, and at the same time, please note here it's an and at the same time x square also has to be less than or equal to 3. Now you can either solve these inequalities on your own. My students just do these kinds of inequalities mechanically. So whenever they see x square is less than or equal to a number, they write the solution as x lying between the square root minus the square root of that number, comma the square root. So if x square is less than or equal to 3, you can either solve it using the sign diagram, or you can simply write that x belongs to the interval minus root 3 to root 3, or x lies between minus root 3 and root 3. Our other inequality here on the left is x square is greater than or equal to 1, and in this case x will lie beyond 1 or to the left of 1. So x belongs to the interval minus infinity to minus 1 union 1 to infinity. Again, we're not done yet. We have one more step to go, and after that we will get the solution. So the point here is that both these expressions for x must be satisfied at the same time, because it's an and here in between. We have to take the intersection of the solutions of these two inequalities. And if you notice here, the blue line on this number line gives us a solution for x square greater than or equal to 1. So this is showing that x is either to the right of 1 or x is to the left of minus 1. And similarly, the solution for x square less than or equal to 3 is given by the green line, which is going from minus root 3 to root 3. And you can see here that the intersection of these two solutions lies between minus root 3 to minus 1 or between 1 to root 3. So our solution in this inequality, for this inequality, would be x that belongs to the interval minus root 3 to minus 1 union 1 to root 3. Right. The next example asks you to find all real numbers x that satisfy mod of x plus 1 greater than 2. So here we will use the result that when mod of x plus 1 is greater than 2, that means that the expression inside the absolute value sign is either greater than 2 or it is less than minus 2. So x plus 1 greater than 2 or x plus 1 less than minus 2. Now if we solve for the inequality on the left, we get x is greater than 1, and the inequality on the right gives us x is less than minus 3. So our solution will be x greater than 1, so 1 to infinity, or x less than minus 3, that is x lies between minus infinity to minus 3, the union of these two intervals. The next inequality is an interesting one. It asks you to solve for x, the inequality 1 plus 3 by x, the absolute value, is greater than 2. Again, at the outset, let us rule out division by 0, so x can't be equal to 0. And we'll use the property of absolute values. So absolute value of 1 plus 3 by x greater than 2 means that this expression 1 plus 3 by x is either greater than 2 or it is less than minus 2. Now let us solve these two inequalities separately. The left hand side inequality says that 3 by x has to be greater than 1. Now because 3 by x has to be greater than 1, clearly x here has to be positive. That is one piece of information. Now taking the reciprocals on both sides will reverse the inequality, because I have to solve for x, I am taking reciprocals. So I'll get x by 3 is less than 1 and therefore x is less than 3. But because x is also positive here, my solution for this part of the inequality is x lies between 0 and 3. Now in the second inequality, I have 3 by x is less than minus 3. If you see where my cursor is pointing, I can cancel out the 3's to get 1 by x is less than minus 1. Now because here 1 by x is less than minus 1, x has to be a negative number. So that is one piece of information. And at the same time, if I take the reciprocals for this inequality, on the left hand side I'll get an x, and on the right hand side I'll still have a minus 1, but I'll have to reverse the inequality here once I take reciprocals. So I get x is greater than minus 1, but at the same time x is also less than 0, so x lies between minus 1 and 0. And combining these two inequalities gives us the solution as x that lies in the interval minus 1 to 0, these are open intervals, union 0 to 3. This inequality here in example 11 is 3 divided by absolute value of 2x minus 1 is greater than 4. Again, at the outset, let's rule out division by 0. So here we have in our solution that x cannot be equal to half. Also, because the absolute value of a number is always positive, here I can very simply cross multiply by 2x minus 1, or multiply both sides of the inequality by mod of 2x minus 1 to get 3 is greater than 4 times mod of 2x minus 1, or mod of 2x minus 1 is less than 3 by 4. And now I can use my property of absolute values, which is that 2x minus 1 has to be has to lie between minus 3 by 4 and 3 by 4. But I'm not done yet, because I still have to solve for x. So if I add 1 to all the three expressions. On the left I'll have minus 3 by 4 plus 1, which is 1 by 4, which is less than 2x, which is less than 3 by 4 plus 1, which is 7 by 4. And this in turn implies if I divide by 2 throughout, I get x lies between 1 by 8 and 7 by 8. But note here that because in our inequality x can't be half, so the solution is given by x belonging to the open interval 1 by 8 to 1 by 2 union the open interval 1 by 2 comma 7 by 8. Now this is as far as the inequalities involving absolute values are concerned. In the little time that I have left, let's look at some inequalities that involve square roots, because I also talked about square roots in this lecture. So this is an inequality that we tested the students for in one of the university exams. And if you notice here, all the expressions, so again at the outset rule out division by 0, so x can't be 3. Also, we have to have all these expressions under the square root non-negative, because if you remember I said we do not consider square roots of negative numbers. So we must have x plus 4 greater than or equal to 0, and at the same time x minus 3, but x minus 3 has to be strictly greater than 0 here, because we have ruled out x equal to 3. And at the same time 3 minus x also has to be greater than or equal to 0. So all these three inequalities must be satisfied at the same time, which is to say x is greater than or equal to minus 4, and x is greater than 3, and x is less than or equal to 3. But the problem here is that you can't have x being both greater than 3 and less than or equal to 3 at the same time. So this is a situation where there is no value of x that satisfies this inequality. The solution is the null set. And now for one more final example for inequalities, this asks you to find all real numbers x that satisfy x upon square root of x square plus 1 is greater than x upon square root of x square minus 1. Again, we'll rule out division by 0, so that x can't be plus or minus 1, because if you notice here, x square plus 1 here in the denominator on the left hand side, that is always positive, but x square minus 1 could be 0 for x square equal to plus minus 1. So we don't want division by 0, and we'll rule out x equal to plus minus 1 as part of the solution. Also note here that anything under the square root has to be positive. So x square minus 1 has to be positive here. It's in the denominator, so positive, which in turn implies that x square is greater than 1. We don't need to do the exercise, by the way, for x square plus 1, because x square plus 1 is already positive under the square root. Now, if x square is greater than 1, this implies that x lies either to the left of minus 1 or to the right of 1. Now, please also note that this is an inequality. If you just stare at it hard enough, this is an inequality which will not be satisfied for an x that is greater than 1. And why is that? This is because if you look at the denominator on the left hand side, the denominator is square root of x square plus 1. And the denominator on the right hand side is square root of x square minus 1. And you can clearly see that the denominator on the left hand side is greater than the denominator on the right hand side. So clearly, when I divide by a higher number on the left hand side, if x is positive, then the entire left hand side will become less than the right hand side. So because square root of x square plus 1 is greater than the square root of x square minus 1, this particular inequality does not hold for x is greater than 1. Which means that in this particular set of intervals, minus infinity to minus 1, union 1 to infinity, we are going to look for our solution only in the interval minus infinity to minus 1. Now let us see how this will work. So we have established that x upon square root of x square plus 1 is greater than x upon square root of x square minus 1, and this inequality holds only for a negative x. Now, because we are working with a negative x, we can we can square both sides of the inequality. The idea being that we want to get rid of the square root signs on both sides. So, if I square both sides of the inequality, I get x square upon x square plus 1 is less than, the squaring will reverse the inequality. So, x square upon x square plus 1 is less than x square upon x square minus 1, and because the x squares are positive numbers, I can cancel them to get 1 upon x square plus 1 is less than 1 upon x square minus 1. And you can see that this is always going to be true, because x square plus 1 is a denominator for the left hand side that's higher than x square minus 1. So, therefore, the left hand side, the reciprocal of x square plus 1 is always going to be less than the reciprocal of x square minus 1, which is to say that the inequality will be satisfied for all values of x that lie between minus infinity and minus 1. There is no contradiction with that particular interval. So, that is our solution for this particular example. Let us now do a quick example, which is actually a word problem. So, here this is a problem from Sitzsater and Hammond. So, let us suppose that there is a 5 meter iron bar that is to be produced, and it is necessary that the length, so you have to produce an iron bar which has a length of 5 meters, but the length should not deviate more than 1 millimeter from its stated size, that is from the size 5 meters. So, the question asks you, write a specification for the rod's length in meters by using the absolute value sign and also by using a double inequality. So, here we have that because the length of the rod cannot deviate from 5 by more than 1 millimeter, let's denote the actual length of the rod by x, and that deviation, the x minus 5 deviation should not be more than 1 millimeter, which is 0.001 meters. So, in absolute value terms, this would be mod of x minus 5 always has to be less than 0.001. And in terms of a double inequality, if I solve this inequality, I'll get minus 0.001 is less than, x minus 5 lies between minus 0.001 and 0.001, and solving for x will then give me x lying between 4.999 and 5.001. So, this is all I have to discuss for today's lecture. Since we are running out of time, we'll close the discussion here. In the next lecture, I will be starting with the topic logic, and this is something which is very interesting and useful for anyone who's training to be an economist. So, do tune in, and thank you very much for joining us today. Bye-bye.
Thank you so much, ma'am. Thank you for such interesting and enlightening lecture. Dear friends, thank you so much for watching us. If you have any query, any suggestion regarding our lectures, please write us back on info.cec@gmail.com. I repeat, info.cec@gmail.com. Stay tuned, keep watching. Thank you so much. Thank you so much, ma'am.
Thank you, Asmita. Thank you.